How's it going, guys? In this video we're going to go over how to use intermolecular forces to compare boiling point and vaporization point of different compounds and elements. So first off, I'm going to put this down. We had gone over that in the last video, so if you're not familiar with some of these intermolecular forces, it's probably a good idea to just review that video. So for basically, you can use these steps in any order, but this is the way that I think it's easiest to compare boiling point and vaporization point. So 1, consider the intermolecular forces of both compounds or elements that you're comparing. Because essentially what it's going to be is, we'll kind of get into it with some of the examples, but basically if the compound has more stronger intermolecular forces, then that's going to affect it. And we're going to get into how later. But essentially you're trying to find out which one has stronger intermolecular forces. Now consider molecular weight and molecular geometry of both. That's going to play into. And then finally, at room temperature, molecule with lowest boiling point should have the highest vaporization point, and vice versa. So that's, I think, a pretty important one to keep in mind. Oftentimes you can be asked, like on the same set of problems or even in the same problem, which of these two has the higher boiling point, which one has the lower boiling point, or which one has the higher vaporization point, or whatever. Essentially, if you can find one of those things, you can find all of them just by association. So I think that it's going to be we're going to go a little bit further into this, but we'll start off. I'll scoot this down, and we'll start off with 1. Which one has the higher BP? We're going to have C4H10 versus C2H6. And I think we might have actually done this exact one in the previous video. But what I like to do is really quick, consider the intermolecular forces as my step 1. We're looking at both of these. They're just both carbon chains. They're organic. Neither one's going to have any intermolecular forces other than dispersion. So then we can skip right to the drawing. 1, 2, 3, 4 carbons. 4, 5, 6, 7, 8, 9, 10. So it's just a simple chain. So here we go. We have just 2 carbons. 1, 2, 3, 4, 5, 6. And now we have both of our structures. I mean, these don't have to necessarily be exact, but it's, you're getting kind of a doodle down there to help guide your thoughts. So here we go. Both of these have just London dispersion. Okay, so now we've gone through step 1. We compared, and again, these aren't in any specific order, but I think this is just the order I like to do them in. Intermolecular forces are identical, so let's move on to number 2. Consider the molecular weight and molecular geometry. So in this case, the geometry is not really relevant because they're essentially equivalent. They're both chains. But obviously the molecular weight, the molar mass of this is going to be much larger. So this kind of has the favor for now. And then we're going to use kind of that last step there, number 3, which you can kind of still see to basically inform our decision. So because C4H10 is bigger, it's a larger molecule. There's more molecules in that, or sorry, there's more atoms within this compound that are contributing to the London dispersion force. So the London dispersion force is higher, i.e. the IMF is more, it's greater, even though it's the same type. So what you could say that as, it's easier to distort the electron cloud. Or it's more polarizable. It's kind of a weird word, but sometimes you have to explain in words exactly what you mean by one having a stronger this or that. But essentially, it's easier to distort the electron cloud. This is going to have the higher boiling point because essentially there's more forces at play here, and it's more difficult. So that's the answer to that one. Now we're going to have scoot down to number 2. And this one is going to be, let's see, which one has the higher boiling point again? We have H2O versus hydrogen peroxide. H2O versus H2O2. So first off, like I said, I like to draw them. So I have our H2O, and then our H2O2 is going to be like this. Okay, so we kind of have both of our drawings. We've done that kind of first step. We'll compare now the intermolecular forces. So over here we're going to have dispersion. Now here we have we're going to have the dipole. I believe that they both will have that in this case. And then we have the hydrogen bonding. So again, we're at that crossroads. So in theory, if one of these had the ion dipole and the other didn't, the one with the more the more stronger forces or the more number of forces, and I think it's pretty much always going to go in this direction. So for instance, if they have ion dipole, they likely have the dipole and London dispersion and everything leading up. Regardless, they might have hydrogen depending on if they have the FO and the N. But you're going to look at this, compare the forces first, and then, okay, we compare the forces. Now we're going to look a little bit more closely, so we know which forces they have, but which ones are stronger. Now, there's two possible, basically you have the one oxygen, that's hydrogen bonding here. Here you have two oxygens that can both contribute to the hydrogen bonding. So there's two separate oxygen molecules that are hydrogen bonded. And there's also a total of more molecules, which means that the total dispersion force is going to be greater, and the hydrogen bonding there's more of them. So if you're comparing even larger molecules, you might want to look at how many hydrogen bonds there are, and then that's one way to inform your decision. So in this case, H2O2 has more electrons, which means more polarizability. Stronger LD forces, and greater dipole moment. Now we're going to move down to the last one that we have. And you know what? I think there's not really going to be enough room there, so we'll put it over here. So, higher vapor pressure. We have HOOH or HSSH. So first off, like I said before, I like to always draw it. I'll kind of segregate off this part here. First we have HOOH, and for this, I think there's a triple bond there. So then for the HSSH, it's going to have that. So there we got our structures. Now we have up here hydrogen bonding, dispersion, we'll have dipole, and we have London dispersion. Now here we have dipole-dipole, and we have London dispersion. But it's not FO or N. We do not have hydrogen bonding here. So we've got a clear difference. However, now we have to look at them based on that rule up here, number 3, which I think is very important. At room temperature, the molecule that has the lowest boiling point should have the highest vaporization point. So in this case, the HOOH, it's got the stronger, it's got the stronger intermolecular forces. It's greater polarizability, and it's easier to distort its electron cloud. Those are kind of the main lines, I guess you could say, when you're making a written explanation. So for that case, it'll have the higher boiling point, which means it has the lower vaporization point. So now for HSSH, we're going to have the lower boiling point, but we're going to have the higher vaporization point. So that's going to be our answer. So yeah, that was kind of just like a brief overview of some of these. Again, these are kind of the steps that I use, but you don't have to do them in any particular order. I think this is what makes the most sense to me, though. And just make sure you're acknowledging all of these factors. Intermolecular forces being probably the most important determinant. But then, you know, if that doesn't lead you to an obvious answer, then I would move forward to consider the geometry, the molecular weight. But usually, if you can draw out the structure, then you're pretty well suited to, you know, be able to apply this to the molecules and figure out which forces are at play there. So yeah, I hope this helps someone.